everyone, my name is Maria Giulia, and today I will be talking about differentiation. Here you can see my name and you can also see my email address, so please feel free to contact me, send me an email if anything is not clear or you need any sort of information. I will try my best to reply as soon as I can. You can always send me an email. Of course, I will also be available on the 21st of August during the actual online session for this class. And in that case, in that occasion, I will also be able to answer any question that you may have. But just in case you do not feel comfortable or you cannot for any reason, send me an email. Or maybe you want a clarification as soon as possible. Always feel free to send me an email. So, differentiation is something that you have encountered already many times, probably. So, this is just a refresh. You already know that the topic is very wide, it's also very important because you have probably used differentiation not only in your calculus classes but also in your physics classes and probably other types of classes as well. So it's one of those topics that are really of crucial importance. It's really important to understand differentiation, understand the meaning, the geometric interpretation in particular, and also it's important just knowing how to actually compute a derivative. So you probably know better than me how wide this topic is, and it's impossible to cover every single thing that there is to be said in just a few videos or a few slides. But I have made a selection of the things that I think are important to refresh. And this is what we will be talking about. So I will start with introducing again the secant and tangent lines. It's just a refresh, just so that we kind of set the context to be talking about derivatives. We will then talk about derivatives and rates of change. So what is a derivative? What kind of information does it give me? We will be talking also about the application in physics, more specifically about velocity. Derivatives actually do come up a lot in physics classes, dynamics classes. I was using derivatives a lot. We will also talk about the derivative itself as a function and what that implies, the domain of such a function, the continuity of such a function, and so on and so forth. We will also briefly touch upon higher order derivatives, so second derivatives, third derivatives, and so on and so forth. Then we will talk about differential rules, so everything that you need to know to actually compute the derivative. So after we basically talk about the theory behind it and the meaning behind it, we then actually discuss the tools, the practical tools that you need to actually just compute the derivative. So we will be talking about the derivatives of a constant function, an exponential function, a logarithmic function, and so on and so forth. And we will also give proofs. And then finally, we will be talking about a very important application of derivatives, and that is analyzing a function both globally and locally and finding the maximum and minimum values using derivatives. So in this first video, I will actually not be covering every single topic. So I will split the videos in multiple parts so that it's easier to follow, or at least I hope. So we start with what a secant line is. So we have a graph, and this is just a generic graph. There isn't a particular reason why I chose specifically this graph. But the idea is that the secant line is a line passing through 2 points, P and Q, of an arbitrary curve, which is described by a function. So, by an expression, y is equal f of x. So, what is important here is that the secant line cuts the graph through 2 points. So here we have the 2 points defined, and then we have, of course, these 2 points belong to the curve, and there isn't a reason why I chose specifically these 2 points. Any 2 points would have been also valid, so I could have also chosen a point here and a point here, and then just draw a line that goes through those 2 points and therefore cuts the graph. So this is a secant line. Now, what's interesting about the secant line is the fact that considering that we are defining it as a line that goes through 2 points, it's very easy to find the slope, right? So the slope of a line is just the famous rise over run. So m is equal to delta y over delta x. So if we have this, if we have these 2 points, let's say that I call this point x1, y1, and I call this point x2, y2, I define the slope as the difference in the y values. So in this case, it would be y2 minus y1 over the difference in the x coordinates. So that would be x2 minus x1. So this is simply the slope. In this next slide, I've actually just called the 2 points in a slightly different way. I have called, let's see, it does, of course, it does not make a difference whatsoever. It just gives a more maybe formal definition of slope, but the idea is that I call this point x f of x, and then I call this point x plus delta x, and then f of x plus delta x, right? So the idea is that I define this point, this one here, and I call it x f of x, those are the coordinates, and then I define the second point having x coordinate x plus something. So I'm adding to the x coordinate something, a little displacement delta x. And then of course the y coordinate will be f evaluated at that point. So in this case, it's exactly the same. It's just a matter of the way we define the points and the way that we choose the coordinates. But in this case, our m would be the difference in y coordinates again. So it would be f of x plus delta x minus f of x over x coordinates of the second point would be x plus delta x minus x. So of course these two cancel out, and then we're left with the slope of f of x plus delta x minus f of x over delta x. So far we have just defined the secant line, and we have said that finding the slope of this line is particularly easy, and it's something that we can readily do because we have 2 points already. So we can just apply this formula and easily find the slope. So this is what I did here. This is the formula for the slope. So something that is important about a secant line is the geometric interpretation. So the slope of the secant line is the average rate of change of the function in a certain interval that we are considering. Now in this case, the interval that we are considering, we're going from x to x plus delta x, right? So basically the slope of this line is telling me how on average the function is changing within this specific interval of choice. So we will see this later when we talk about the applications in physics, but this is the famous average velocity, right, that we can use in physics. So we are interested in the average rate of change of the position function, and in that case, basically that average velocity is indeed the slope of a secant line. So this geometric interpretation, I think, is important to remember, or useful to remember. So average rate of change of a function within a specified interval. What about a tangent line? A tangent line is a line that touches an arbitrary curve at a point P. So again, we have the same curve. Let's say that this is the point P. So this is the tangent line in green. So it just touches the function at this point P. So the key difference here is that I do not have a second point anymore to rely on when it comes to finding the slope of this line. So now the slope of this line is of great interest, and we will see why. So the dilemma here is, how do I actually find the slope of this line? And something that is interesting, so let's see. Make a little drawing here. So let's say that I have a function here, and I define a point P, and let's see what the tangent line looks like. Would be something like this. I want to find the slope of this tangent line. One approach, which may sound naive, but is actually based on what I already know, is just starting from what I know. So the idea would be, okay, I know how to find the slope of a secant line. So I know how to find the slope in the case in which I'm given 2 points. So let's say that I actually consider another point on the graph. Okay, let's call this Q. Now let's give a few, let's say that this has x coordinate A, and therefore this would be, let's see, this would be f of A. And let's say that this other point has a x coordinate, we just call it x. So this would be all the way here. This would be f of x. So now I ask myself, what happens if Q, this point that I'm arbitrarily choosing, gets closer and closer and closer to P? So basically the strategy that I want to use is something like, okay, I know how to find the slope when I'm given 2 points. I don't know how to find the slope when I only have 1 point, but I can consider the slope of the tangent line very similar to the slope of a secant line that passes through 2 points that are very, very close to one another. So I'm cheating a little bit, basically. I'm trying to kind of rephrase the problem, or bring myself back into something that I do know. But that is the idea. So what happens when this point Q gets closer and closer and closer to P? In other words, what happens when this X gets closer and closer and closer to A? That is what I'm basically asking myself. And what happens in that case is actually that. So as X goes to A, the point Q goes to the point P, basically. And the slope of the secant line through the points PQ gets a better and better, becomes a better and better approximation of the slope of the tangent line at the point P. So basically, this idea of, okay, I want x to become closer and closer to a, that should ring a bell, and that bell is called a limit. So limit as x goes to a of what? Of basically the slope, right? Of this secant line. So the slope of the secant line again is delta y over delta x. So the delta y would be f of x minus f of a over the difference in x coordinates. So that would be x minus a. So the limit as x goes to a of f of x minus f of a over x minus a, this expression should give me the slope of the tangent line that passes through P. This is basically the idea. Another way of so this is basically the definition. We will actually see it in the next slide. So this is an important concept. So we want to find the slope of the tangent line through P. We don't know how to do that. We say, okay, how about I get really close to that by choosing a second point, we called it here Q, which is so close to the first point that basically the slope of the secant line becomes a really good approximation of the slope of the tangent line. Another way of seeing at it, of looking at it, and you have probably seen this, is, well, it's just a matter of notation. So the concept is exactly the same, but sometimes what we do is call this interval h. So in that case, this point we actually call, instead of calling it x f of x, we define it in terms of a. So we say, okay, the coordinate I'm going to call a plus h. So a is the starting point plus a certain displacement, which is h. And then the y coordinate, of course, will be f evaluated at a plus h. So this is the coordinate of this point. And in this case, x going to a is the same as saying that h goes to 0. So what happens when the distance between a and x becomes smaller and smaller and smaller and smaller? So again, that rings a bell. It's a limit. Limit this time as h goes to 0. And again, of the slope. The slope will be again the difference in the y coordinates. So in this case would be f of a plus h minus f of a over x minus a we have called h. So these two, I don't know where the colors are. Well, oh, here they are. Okay, so these two colors, these two expressions, this one here and this one here, they are exactly the same thing. It's just a matter of notation. It's just a matter of how we define things. And in fact, you can actually go from one limit to the other just by performing a change of variable. More specifically, by setting h equal to x minus a. Right? So the idea is that if you do this change of variable, as x goes to a, h goes to 0, as you can clearly see from here. And in fact, this x would actually become h plus a, which is what you find here. So this is basically the idea. So let's look at the slide. So in order to find the slope of the tangent line, we need to know how the slope of the secant line behaves as the second point approaches the first point. So what happens when Q gets closer and closer and closer to P? That is the idea. And the definition, so the slope of the tangent line is so important that we have actually dedicated an entire section. It's actually called the derivative. We will see this. But the idea is that the tangent line to the curve at this point, a f of a, is the line through P, which has this slope. Limit as x goes to a of f of x minus f of a over x of a. Or again, you can write it with the expression as h goes to 0. It's exactly the same. Now, I would like to draw the attention to something that is really important. Provided that this limit exists. This limit does not always exist. Limits are not obligated to exist. Sometimes it does, sometimes it does not. And this is really important to realize. So this is basically exactly what I was saying. So as x goes to a, the second point gets closer and closer to P. So the slope of the secant line becomes more and more the slope of the tangent line. And this is the note that I was referring to. So you can either state the definition as formulated here, so as x goes to a, or as h goes to 0. It's exactly the same idea. It's exactly the same thing. Okay, we have an exercise. Find the slope of the tangent to the curve y is equal 1 over square root of x at the point where x is equal to a. So we have literally stated here the definition of such a slope. So it's a limit, again, provided that it exists. So in this case, for instance, I have written it as the second definition, so as h goes to 0 of f of a plus h minus f of a over h. So we plug in, our f is 1 over the square root of x, so evaluated at a plus h, it becomes 1 over the square root of a plus h minus f of a, that's simply 1 over the square root of a, everything over h. Now, these exercises I really like, and I actually included quite a few because they give the opportunity to practice your limits. This is important. Limits are important. You always deal with limits, so it's good to refresh. In this case, the smart approach to this limit is to manipulate somehow this expression. More specifically, it would be really nice if we can rewrite somehow the numerator. So we can rationalize it. How do we rationalize it? We multiply and divide by this expression, but instead of the minus, we put the plus, right? So here I multiply and divide by 1 over square root of a plus h plus 1 over the square root of a. So once I do that, this expression here just becomes, it basically becomes the first term squared minus the second term squared. So if I square them, I basically just have 1 over a plus h minus 1 over a. And this is what I have at this point here. I do a little bit of, I just put everything into a common denominator, and I do the same at the denominator as well. I will have a few things canceling out, and then this is what I get to. Now at this point, h and h, they cancel, and here you notice that you basically have the square root of a plus h over a plus h. So this is equal to a plus h to the power of 1 over 2 minus 1. So this is basically a plus h to the power of negative 1 over 2, which can also be written as 1 over the square root of a plus h. So this is why we actually find it here at the bottom. The same thing we have actually done with the square root of a. So over here I have square root of a over a. This becomes 1 over the square root of a, which is again what I find here. And this is just this actually stays the same. Of course, this h gets cancelled with this h and this h as well. So the inner step will be here, you factor out the h. There we go. And then you cancel it out with this h on top. Sorry, I should have maybe explained that more. Once you have come to this expression, you can just evaluate it. So to evaluate it, you plug in 0, where you see the h, and you basically end up with -1 over square root of h times square root of h times 2 square root of a. So this is equal to 2 times a to the 3 times 1 over 2. And this is our answer. So this is the slope of the tangent to this curve at a general point, where x is equal to a. Yeah, we could have also write it as it's just a matter of preference, but this is completely fine. So the second part of the equation asks me to find the equation of the tangent line at point 1, 1. This is very easy because once I know the slope, so this is the general formula of the slope. In this case, my a is equal to 1. So if I plug in here 1, I basically just get -1 over 2. So my slope in this case is -1 over 2. And then I can just use very simply the equation of a line through a point. So that would be y minus y0 is equal to m times x minus x0. My y0 is the y coordinate of the point given, so this would be 1. This is my slope, which is -1 over 2, and this is the x coordinate of the point given, which is also 1. So yeah, this is basically what I get. So this is the expression with everything plugged in, and then you can work it out and have this equation line. Okay, now we have talked about tangent lines, secant lines, the idea behind how to find the slope of the tangent line. Turns out again that this slope of this tangent line to a point is so important that we have given it a name, and that is derivative. So we now introduce for the first time the term derivative. So the derivative of a function f at a number a, denoted by f prime of a. We will be talking about notation. This is just one way of expressing this. There are many ways that you can indicate notation-wise the derivatives. I will be using them interchangeably because I don't really have a strong preference. So sometimes I use one, sometimes the others. But it's good that you know all of them. And again, so the derivative evaluated at a, so f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a over h, provided that this limit exists. So this is exactly what we have been talking about. The only thing that we are introducing here is that we are giving this expression a name, and this name is derivative. But again, it's the slope of the tangent line at x is equal to a, at a number a. Now, I would like to stress even more this part here, if the limit exists. Let's say that we are considering the function absolute value of x. So we have this exercise. They tell us f of x is equal to the absolute value of x. What is f prime of 0? So what is the slope of the tangent line at x equals 0? Or the derivative evaluated at x equals 0. Now, we just start by writing our definition. F prime of 0 is equal to the limit as h goes to 0 of f of a plus x, but in this case, our a is equal to 0 because we're trying to find, so in this case, f prime of a is equal to f prime of 0. That's what we're trying to find, right? Minus f of 0 over h. Now, f of 0 plus h is just f of h. And so that's going, we plug it in and we have the absolute value of h. Minus f of 0, now the absolute value of 0 is simply 0 over h. So we actually have come to this expression right here. This limit, I am sure that you have all seen multiple times probably in your life because it's one of those limits that you just encounter and is just kind of famous in its own way. Why is it famous? Because it does not exist. Why does it not exist? It does not exist because this limit is different, it gives you a different result depending on how you approach the point. So the idea of the absolute value of x is that if you approach this point from this side, the function behaves differently with respect to what happens when you approach the point from this side. So in other terms, if you calculate the limit as h goes to 0 from the right, so this is basically a limit from the right, that's going to yield a different result than the result that you would get if you approach the limit from the left. And if you, as you probably remember, this is exactly the way that you prove a limit does not exist. How do you prove a limit does not exist? You just show that the result depends on the path that you take. And this, by the way, is true in one variable, but it's also true in multiple variables. Now, I will not be dealing with derivatives in multiple variables. A colleague of mine is doing that already, but as you have probably already seen from that video, you will see how do I prove? Well, I just show you that depending on the path that I take to get to that point, I'm going to get different results. That is how you prove that a limit does not exist. And in one variable is the same. If I take this path, so if I walk along this way or I walk along that way, the function behaves differently. And therefore the limit is going to yield different results. So more specifically, if I approach it from the right, the absolute value of h is equal to h. So I have h over h, that is 1, right? So if I take the limit, that's going to just yield 1. If I approach it from the left, that actually becomes negative h. So negative h over h, that's negative 1. The two are not the same. This means that the limit does not exist. So this is just to stress, this example will come up a lot. Even when we will be talking about continuity, it's just important. So just do not take for granted, do not just assume that a derivative exists at all points, because sometimes that's just not the case. So here, now that we have introduced finally the word derivative and what that means, we now give a more formal definition of the equation of a tangent line. So before we knew what derivatives were, let's put it this way, we have just found the slope of the tangent line. We didn't call it derivative, but basically that's what it was. And then we found an equation by using the fact that we knew the slope and the fact that we know how to find the line through a point. And that is basically how we found the equation of that tangent line. Now we are basically given so it's the same thing, just worded differently. So we have, this is the equation, y minus f of a equal f prime of a. So this is the slope. This is the slope that we were talking about. This is the derivative of a function evaluated at a times x minus a. So basically this is our x0 and this is our y0. So it's basically exactly the same that we did before. This is just a different way of looking at the same thing. Now that we have gained the knowledge of what the slope of this tangent line is, we call it a derivative. So how do I go about finding the slope of this tangent line? I have to find the derivative at that point. So in this exercise, we're asked to find the equation of the tangent line to this curve at the given point 1, 1. So really, of this expression, we need to find the salient point. The most crucial point is finding this expression, and we know the definition. We know how to define that. Is the limit as h goes to 0 of f of 1 plus h, so this is our a, but since the point is 1, 1, we know that a is equal to 1, minus f of 1 over h. We plug in, so we basically need to evaluate the function at 1 plus h, so this becomes 2 times 1 plus h plus 1 over 1 plus h plus 2 minus f of 1. If we plug in 1 here, this just becomes 3 over 3. So that's just 1. That's why you have this negative 1 over here over h. And here's just a matter of algebraic manipulation. You just put everything under a common denominator and you get here basically. You get to this limit and well, this limit is equal to 1 over 3. Why is it equal? Well, maybe I should explain it a bit better. So if you actually manipulate it a bit further, this becomes the limit as h goes to 0 of 1 over 3 plus h. And then you evaluate it, and well, if this goes to 0, this just becomes 1 over 3. In this case, I actually wanted to play with both expressions just to prove that they are perfectly equivalent. You can use which one you prefer, which one you think it's most convenient. Sometimes you just see a problem and you say, well, actually, this variable is more handy to use. I mean, it's exactly the same reasoning behind solving exercises by a change of variable, for instance. So in this case, I have also redone the exercise using the other definition, but it's exactly the same way of proceeding. You just need to be careful here because your limit is going to a, so it's actually going to 1. It's not going to 0. Something important that I'm thinking about right now, again, you probably are really good at limits, but just remember that you only evaluate the limit once. I used to see this sometimes when I was a TA. You do not evaluate the limit once. For instance, like you plug in, you have f of x, for instance. Okay, so you do a little bit of manipulation of f of x, then you plug in h is equal to 0, and then you do another bit of manipulation. Don't do that. In a few cases that will actually work, but that's just a coincidence. So first you do all types of manipulations that you need to do on the limit, and then your final step is to evaluate the limit, plug in 0 or a or whatever it is that you need to plug in, and then you give the answer. Please don't make that mistakes, because it's really sad. So once we found the slope, then it's very easy. We just plug in here. We have y minus f of a, that's the y coordinate of our point. So minus 1 is equal to the slope, or the f prime evaluated at a, that's 1 over 3, times x minus the x coordinate of the point, which again is 1. And this is the equation. This is the equation of the tangent line that we were looking for. Now, application in physics. Now, we now want to talk about the application in physics. So we have seen the theory, we have talked about these very important lines, their slopes, and now we just revisit everything in the context of physics. More specifically, we are talking about velocity. So if you remember at the very beginning, when I was talking about the secant line, I said that the slope of the secant line has a very important meaning, and that meaning is actually the average rate of change. So the average rate of change of a function within a specific time interval that we are, well, actually I was just saying an interval. In this case, we're going to be talking about time intervals that we are considering. So here we have this very famous formula, average velocity is equal to the displacement over time. And so we suppose that we have an object, this object is moving along a straight line, and the movement of this object is actually described by this equation of motion. So S is a function of time. So what it means is that this gives us information about the position of the object at each time point. So if we want to know the position of the object at time equal 5 seconds, we just plug in 5 and we have the position of the object. Now, it turns out that the average velocity is the slope of the secant line that goes through 2 points. More specifically, if we look here at the, this is just a sketch that I made. So let's say that this is our S, so it's a function of time, it's dependent on time. Here we have t, and we are considering 2 points here. This first point as x coordinate a, and then s of a as the y coordinate, and after a certain amount of time has elapsed, so after a certain delta t, we now have another point. So the object has another position, of course. And this the second point as coordinates a plus h, s of a plus h. So now let's compare it to this formula that we all know, we're all familiar with. Let's just try to interpret it on the graph. The displacement is the difference in between the final position of the object and the initial position, right? So the displacement is actually this difference here. It's the delta y. It's basically the difference between the y coordinate of the final point and the y coordinate of the first point. The time, this time, so the denominator, is basically how much time has elapsed between the first and the second points that I'm considering. So it's the time interval that I am interested in. So delta t would basically be a plus h minus a, that we have called h. So this is basically exactly what we were talking about at the beginning, but now it has been revisited. So if I want to find the slope, it's going to be displacement over time. So again, the slope of the secant line, because I am considering this line, well, it should go through these 2 points. I'm considering the slope of the secant line, so it goes through 2 points. And what does it give me? The average rate of change. In the case in which I'm considering, in the special case, in the context in which my function is not any function, but it's the position equation, the slope of the secant line has a particular meaning. It has a specific meaning, and that is the average velocity. So, slope, secant line, average rate of change. That is the average velocity. And here we have exactly, basically you can recognize it, it's the same as before. It's just that we have, I have named here the coordinates differently, because here I'm considering, I said points A, f of A plus H, f of A plus H, but it's basically, it's just a matter of how we call things, but the idea is the same. Now we ask ourselves, just like we did before, what happens if I choose the second point closer and closer and closer and closer to the first point? Well, we now know, because we have talked about it, that if h goes to 0, the slope of the secant line approaches the slope of the tangent line at this point right here, right? This point of the graph. Now, the important thing is, what is the meaning of the slope of the tangent line in the context of velocity? And that is, it gives us information about the instantaneous velocity. So it's not the average velocity anymore, but it's the instantaneous velocity that now we are concerned with. So we have here the formula, V of A, velocity of A, is the limit as h goes to 0 of f of A plus H minus f of A over H. What is that? We have now called this, we have given it a name, it's the derivative evaluated at A. So the derivative of the position function gives me the velocity. This is quite important. So in other words, the instantaneous velocity is given by the slope of the tangent line to the position function at a certain time point. So now we have an exercise just to put this in to practice. Suppose that a ball is dropped from, well, basically a tower, 450 meters above the ground, and we have this equation of motion. We want to know what is the velocity at any time point. So we just say at an arbitrary time point A. We just apply the definition. So the velocity at A is going to be equal to the instantaneous velocity at that time point is going to be equal to the limit as h approaches 0 of f of A plus H minus f of A over H. So now it's just a matter of plugging in. This is our equation. So it becomes 4.9 A plus H squared minus 4.9 A squared over H. Here is just a matter of expanding this out. It becomes this. We can factor the 4.9, and we have this expression within the parentheses. This one cancel, this one cancel. We have 4.9 times H times 2A plus H over H. Now we have gotten rid of the H at the denominator, which was giving us problem, and we evaluate the limit, so we only do it once. This one goes to 0, and we're left with 4.9 times 2A. So this is the expression which gives me the instantaneous velocity of this ball being dropped at any time point. So the velocity. So this is the general formula. So if I want to know the velocity when the ball hits the ground, well, we know that the tower is 450 meters above the ground. So when it hits the ground, then the position function will be set equal to 450 meters. So we can find t. Once we know the time point, we have this expression that tells us, okay, if you plug in the time, I will give you at that time point what the velocity, what the instantaneous velocity is, specifically at that time point. So if we find the time at which the ball hits the ground, we just have to plug in and we find the velocity of the object as it hits the ground, which turns out to be 94 meters per second. So that is basically the idea. So we have this was nothing new. It's just another way of looking at everything that we have talked about. It seems easy, but at the same time, in my experience, in my dynamics class, we were doing this over and over. So a lot of the times you are given this type of equation, so the equation of motion, and then you need to derive the velocity, you need to derive the acceleration. We will be talking about that as well. Sometimes you also have to do the reverse. I will not be talking about differentiation because a colleague of mine is covering that, but of course sometimes it does happen that you are actually given the velocity or the acceleration and you need to find the position, for instance. So those type of this theory actually does come up a lot. So it's important that you know when is it appropriate to use the formula for the average velocity. When is it appropriate to use the formula for the instantaneous velocity? What is the difference, right? So this idea of the limit that comes in is, I think, is very powerful. So that's why I wanted to include it. Not because these things are particularly difficult, but because those are concepts that you want to be sure to have mastered, at least in my opinion. That's why I added them. We now want to talk about, so we've talked about the derivative as the slope of this tangent line at a point B. So we have considered so far the derivative of a function always at a fixed number, at a fixed number a. Now, what happens if we allow this a to actually vary? So we go from a fixed number to a variable. We obtain a function. So basically, we now consider the derivative of a function itself. And this is really important. Like this, I mean, of course, it's something that we are used to, but at the same time, it is important to stress the fact that the moment we consider it a function, we also need to consider that everything that is pertinent to functions also applies. So of this function, we need to define the domain. We need to we can analyze the function globally, locally. We can find minima, maxima. We will have point in which this function is not defined. We will have every single thing that applies to a function also applies to the derivative because it's a function itself. So we basically go from f prime of a, as we have done so far, to f prime of x. So f prime is a new function. It's called the derivative of f. And the domain of f prime is the set of all x such that f prime of x exists. I'm not sure if you're familiar with this symbol, but it means such that. Another way would have been x. Another way would have been even better, would have been all x such that f prime of f exists. Like this. And may be a smaller domain than that of f. So the domain of the original function f and the domain of the derivative are not always the same. And this actually should not come as a surprise because we have seen the case in which f of x is equal to the absolute value of x. So in that case, we actually had a function that was defined on R, and then we found out that the derivative did not exist at x is equal to 0. So in that case, the domain of f prime is not the same as the domain of f. So sometimes they do coincide, so sometimes they are the same, sometimes they're not. So if a function f, which goes from an interval to the set of real numbers is given, we need to find the set, we call it J, which belongs to I, such that f prime of x exists for each x which belongs to J. If J is not equal to the empty set, so if there are x values such that the derivative exists, then we call this new function f prime, and it goes from J to R, and it's called the derivative of f. So in general, J does not have to be equal to I. It can be, but sometimes it's not. In general, a function f is said to be differential at a if f prime of a exists. We have already seen this. How do we go, though, from a fixed number to a variable? We say that a function is differentiable on an interval if basically it's, f prime of a exists for every number a which belongs to the interval that we are considering. So that's pretty basic. So passing from f prime of a to f prime of x in terms of differentiability is pretty intuitive. So we said that it's differentiable at a point a if f prime of a exists. If that is the case, so when we go to an interval, if that applies to every single a which belongs to the interval, then the function is said to be differentiable over that entire interval. Now, the link between differentiability and continuity, I think, is pretty important. And this is something that I want to talk about. We will also do a proof about this. First statement, not every continuous function is differentiable. We have already seen this example. This is exactly what I was talking about, the absolute value. It's continuous on R, but is actually differentiable in R minus this point right here. So this is a case in which the domain of f and the domain of f prime are not the same. So the fact that a function is continuous does not imply that it's differentiable. So if it's continuous in R or it's continuous in a domain that we call D, that does not imply that it's differentiable in D. However, this is where things get interesting. The opposite is true. So differentiability implies continuity. So in other words, basically differentiability is a stronger condition. So if a function is differentiable in a certain interval, then we know that it's also continuous in that interval. But the other way is not obvious, or is not guaranteed. So basically continuity is a necessary condition for differentiability, but it's not sufficient. So every function that is differentiable is also continuous, but not every function that is continuous is also differentiable in a certain interval or in a certain domain. How do we prove this? This is a very interesting proof, and I'm going to go over it with you. Follows the proof. We know that the function f of x is differentiable at the point x is equal to a. What we want to prove is that this implies continuity. So we want to prove that f of x is continuous at the point x is equal to a. This means that the limit as x goes to a of f of x is equal to f of a. I hope that you can recognize this as, this is literally the definition of continuity of a function at x is equal to a. Now, for a moment, let's actually reflect on this information that we have. This is what we're starting with. This is basically our hypothesis. So f of x is differentiable at x is equal to a. So what this means is that the limit as x goes to a of f of x minus f of a over x minus a, this is what we have been talking about so far, this limit is guaranteed to exist, which is not a given. This is not something that we should take for granted, because as we said multiple times, this limit does not always exist. But in this case, we are sure that it exists. Why? Because f is differentiable at x is equal to a. So we want to prove this, right? Now, we're going to start with what we want to prove, and we're going to do a bit of manipulation on it. So, for instance, we can write this as the limit as x goes a of f of x minus f of a. And ideally, I'm going to write this in red, we want this to be equal to 0. So, what can we do to make this happen? Something that is usually done, it's a very clever approach, is by employing a smart multiplication. So, we multiply and divide by x minus a over x minus a. This is something we are introducing a factor that actually does not change the limit because we are multiplying and dividing by the same thing. But at the same time, this will be a key to employ what we actually know, to introduce our hypothesis. So we can rewrite this as the limit as x goes to a of f of x minus f of a over x minus a times x minus a. So this was just a matter of rewriting it this way. So nothing fancy. At the same time, this is, by the way, there we go. Now, we can split up this limit because, well, it's the limit of a product is the product of the limits. So limit as x goes to a of f of x minus f of a over x minus a times the limit as x goes to a of x minus a. Now, this part, we know it exists. And we're not concerned, well, we will just call this f prime of a. We know that this is something. We know that it exists. Why? Because f is differentiable at x is equal to a. So this has to exist. On the other hand, if we evaluate this limit, we plug in x, and this is actually going to 0. So this entire thing is equal to 0. So we have something that we know exists, times 0, it has to be 0, which is exactly what we want to prove. So this basically ends our proof. So very important to know, differentiability implies continuity, not vice versa. Vice versa is just not true. And then I would say, oh, no, actually we can still keep going for this last part. Notation. Very important point about notation. I think it's important to at least have seen once all of these notations, so that if in a book, a very fancy book, maybe you see one of these, at least you know what it means. I would say this is the one that I've used the most, f prime of x. I use this one, dy over dx, also a lot, or df over dx. This is also something that is I use sometimes, dx f of x. So also know this one. These ones are also pretty used, but you use this when you're talking about a derivative that is evaluated at a. So for instance, dy dx, this means the derivative of y with respect to x evaluated at a. So either with this type of notation or with the square bracket. Either way works. So just make sure that you have seen them. I think this might be the least common, but I actually use this a lot when I am working with more variables. So points of non-differentiability. So we have said that the derivative of a function is not defined in every point in which the original function is defined. So the question is, when does a function fail to be differentiable? So this is a pretty important question. So usually there are three main cases. First one, you can see it here, if you have some sort of corner. If you have a graph in which you have a corner, you can expect the function to not be differentiable at that point. So in this case at a, basically you will not have it will not be differentiable. Second case, we have already talked about this. Continuity is a necessary condition for differentiability. So if a function is not continuous at a, it will never be able to be differentiable at a. So this is basically the case. If you see your function do a little bit of weird things, it jumps a little bit somewhere, at this point, it will not be differentiable. The third point is the point where you have a vertical tangent line. So this means that f is continuous at a, and the limit as x goes to a of the derivative is equal to infinity. So let's actually see an example of this. We consider this function f of x is equal to the cubic root of x, and we consider it at this point here. A is equal to 0. If we try to apply the definition, so we just write limit as h goes to 0 of f of a plus h minus f of a, and so on and so forth. We then plug in, so f of a plus h, this is going to be the cubic root of a plus h. But a is 0, so this just becomes the cubic root of h. F of a, f of 0, 0 to the 1 over 3, that's just 0, over h. So this is what we're left with. So this is h to the 1/3 minus 1, which is h to the negative 2 over 3, or 1 over h to the 2 over 3. So when you actually evaluate the limit, this limit is going to become something like 1 over 0 plus. So it's a plus infinity. So what this tells you is that at 0, the function is not differentiable. We are in this case. Basically here, the tangent line is basically vertical. So, higher order derivatives. The idea is exactly the same. We have done it once, we can do it again, quite literally in the terms. And what I'm talking about is the fact that we have said that the derivative of a function is a function itself. So being a function itself, it can have its own derivative. And how do we find that derivative? We just differentiate again. So if we take f prime and we differentiate it further, we get something that is called the second derivative of f, which is obtained just by differentiating f twice. So that is basically the main idea. So this exercise says if f of x is equal to x cubed minus x, find and interpret the second derivative of f. So about the notation, so you can either do f like that with two prime kind of signs. So this is the second derivative of f. Something that you can also do is this. So it's the second derivative of y with respect to x. I find this notation particularly useful if you're dealing with the third derivative or the fourth derivative. Another one is also this one, for instance. This is the third derivative of f. Or, well, you can also do it like this. But just make sure that you do not actually confuse this with an exponent. I'm saying it because I've seen some students do it. So, what do we do? First of all, we differentiate the function once and then once again. That's basically the idea. So this is something that we have done all along. You just write down the definition. You have limit as h goes to 0 of, so f of h plus x plus h, that's going to be x plus h cubed minus x minus h, and then minus f of x, so minus x cubed plus x, because here we have the signs changing over h. Now it's a matter of expanding this out. I hope that maybe it's a good reminder. A plus b cube, that's a cube plus 3a squared b plus 3ab squared plus b cubed. I think those are nice to kind of remember. You can always derive them, but I think it's just handy to know them, at least this one and, well, of course, a plus b squared. Okay, so once we apply this, we expand this out, we can cancel out some terms, and we also have plus x, minus x, all of those cancel out. And now, and this is the nice part, each and every term at the numerator has an h. So we can factor the h so that we can get rid of the one at the denominator, which is the one that causes problem because we are dividing by 0, right? When we evaluate the limit. So we cancel the h out, we're left with this expression, so this limit, of which, let's see, this one goes to 0 because it has an h, this one goes to 0 because it has an h. That's what you're left with. 3x squared minus 1. Now, So now the key is that we have to do it again. So when we write this time the expression, it's going to be the second derivative of f is equal to the limit as h goes to 0 of f prime of x plus h minus f prime of x over h. So that is basically the key difference. So now we're not working anymore on the original function, but we're working on the derivative. So f prime is 3x squared minus 1. This is the function that we need to use. And indeed, when you evaluate it at x plus h, this becomes 3x squared plus h squared minus 1 minus 3x squared plus 1, and so on and so forth. So this is a pretty simple, because again, this one's cancel out. Here you can just cancel out the h. Oh, let me be careful at just canceling the exponent. This one goes to 0. You have 6x, which is what we expect, even just by doing it at the top of our head. So what about the interpretation of a second derivative? So the second derivative of f is also the derivative of the first derivative of f, right? So if the first derivative was giving us information about the rate of change, the instantaneous rate of change of the function, we now have another function that gives us the rate of change of the slope. So it's the rate of change of a rate of change. So indeed, it's just the rate of change of a rate of change. When it comes to the applications in physics that we were talking about, the velocity, it's actually important to understand the meaning of this second derivative, because it has a name, and that is acceleration. Well, if our original function is the equation of motion, the second derivative is going to be the acceleration. So the instantaneous rate of change of velocity. So velocity is s prime of t. So the way the velocity changes is described by the acceleration. Of course, with respect to time, because we're talking about functions that depend on time. The position depends on time, and so do the velocity and the acceleration. So the derivative of the velocity is the acceleration, or the second derivative of the position is the acceleration. That's it. This is exactly what this is saying. So acceleration, derivative of velocity, or second derivative of position. Another important higher order derivative is actually the third derivative of position with respect to time, which is called the jerk. So the jerk is the third derivative. Here comes this notation that I really like, because I think when you're working with higher order derivatives, it's actually quite handy. Basically, what this is telling you is, how is the acceleration changing? What is the rate of change of the acceleration? So, for instance, how abrupt is your acceleration? So yeah, rate of change of acceleration. So I think this is important. Again, during my physics classes, it does happen a lot that you have to derive one from the other. Sometimes you also have those exercises where you're given a graph and you have to derive the other. So you're given position versus time, you need to find velocity versus time, and all of these elements come in and are really useful. In general, you can take n derivatives of the function, and well, the notation, you can see it here, is just you can write it this way, or you can write it this way. Yeah, all of those are actually valid. Okay. So last but not least, in general, you can differentiate a function n times, and the nth derivative you can express as using this notation, or this one, or this one. Either way works. I really like this ones, just because when if you're solving differential equations, it's a bit annoying to write this over and over again. So this was it for the first part, for the first video. I hope this was clear. I hope this was a useful selection of things that may be useful for you as you start the academic year. If anything is not clear, please, again, reach out to me, send an email, or we can discuss it on the online session if that is needed. The next part will actually be dealing with the differentiation rules. So I know that this one was a bit more theory-based, but that one is really where I added it because I find these things very interesting. I think it's a good way of also practicing limits a lot, which are always useful. But if you want maybe more of a you just want to know the trick how to actually compute the derivative, the next video will actually answer that. So thank you for your attention and for watching this video.